Hi everyone, in this video, we will introduce our paper, Conditional Image-to-Video Generation with Latent Flow Diffusion Models. So given an image and a corresponding class label, we want to develop a class Conditional Image-to-Video Generation framework, which will output a fake video. And the distribution of output videos should be the same as the real video. However, our task is non-trivial. First, different from image synthesis, video is a combination of spatial contents and temporal dynamicals. Second, video generation requires more computational resources compared with image task. To solve these challenges, we disentangle the video generation into spatial content and temporal dynamicals generation. By applying temporal dynamicals to spatial content, we can generate a new video. Based on this disentanglement and considering subject image is given, instead of using class label to generate a whole video, we propose to use class label to only generate optical flow. However, performing warping in the image space is challenging. We need to handle pixel misalignment, occlusion, or large motion. Also, the computational cost for direct generation in the image space is also high. Thus, we choose to perform warping in the feature space. We employ an image encoder to encode the subject image as feature Z. We also design a flow generator G based on diffusion models to generate a flow sequence F hat conditioned on class Y. After warping feature Z using flow F hat, we feed the warped feature to image decoder to generate a final output video. Compared with video and latent feature representation, latent flow has smaller spatial size and only 2 channels. We name our method Latent Flow Diffusion Models, LFDM. To separate the chaining of spatial content and temporal dynamicals generation, we also propose a 2-stage chaining strategy. In stage 1, we first chain image autoencoder part with warping flow. Then in stage 2, we learn how to generate a feature flow from class label. Since these 2 stages are separated now, we can't use the flow here. So in stage 1 training, to do the warping, we also design a flow predictor F to estimate the flow from the real video. This is the training details of our stage 1. Given the subject image and a driving image from the real video, we employ a flow predictor F to estimate the feature flow and occlusion map. Here M is to handle occlusion. We also employ an image encoder phi to encode the reference image as feature map Z. We then apply both flow F and occlusion map M to warp the subject image feature Z and feed it to image decoder to generate output image. And we utilize several conjunction laws to train the models. Note that we don't need any annotation in stage 1. These are the training details of stage 2. For flow and occlusion map predicted in stage 1, we first use the DDPM forward process to map them to be Gaussian noise. In stage 2, we mainly train this DDPM reverse process. Our inputs include the Gaussian noise, the test feature from pre-trained BERT, the image feature from trained image encoder in stage 1, and the DDPM reverse process learns how to map the noise back to the sequence of flow and occlusion map. We employ several conjunction laws to train DDPM. Different from stage 1, to learn flow diffusion models, we need annotated videos. During the inference, we first use pre-trained image encoder phi to encode the subject image S0 as feature map Z0, and use the pre-trained BERT to encode the class label Y as test embedding E. Conditioned on the image feature Z0 and test embedding E, we sample latent flow sequence F hat and occlusion map sequence M hat using DDPM reverse process. Then we utilize the flow and occlusion map to do the feature warping and feed the warped feature to image decoder to generate a final video. We evaluate our methods on 3 datasets: MAG dataset, a facial interaction dataset, MHAD, a human action dataset, and networks, a body and hand gesture dataset. 3 metrics are used, including FVD, which calculates the backshot distance between the distribution of real and synthesized video features, to measure how well a generated video corresponds to the class condition Y and given subject image as 0, we also compute the class conditional FVD and subject conditional FVD. This is one generation example on MARC dataset. This is one example of MHAD dataset. And this is one generation example of NetOps dataset. Here we saw the qualitative comparison of our method against the previous methods. Here we saw the quantitative comparison of our method against the previous methods. Our method can be also easily adapted to new domain face-off videos by simply fine-tuning the image decoder. We also saw a Bayesian study of different sampling strategies. Overall, in this paper, we propose another latent flow diffusion models to achieve image-to-video generation by synthesizing a temporal coherent flow sequence in the latent space based on the given condition toward the given image. Another two-stage training strategy is introduced to decouple the generation of spatial content and temporal dynamics. We also achieve state-of-the-art performance on multiple datasets. Thanks a lot for watching this video. You can also scan this QR code to read our paper online.